Welcome to Git Demystified. Gonna be a fun talk, I hope. Lots of kind of in-depth stuff about what's happening in the world of Git. So I'm gonna give like a brief intro to what Git is and how to set it up. We're not gonna get too crazy there, but we're gonna dive into Git objects, which is how Git is tracking data and remembering changes over the history of your project. And then we'll talk about merging different work streams, so merging two branches, rebasing a branch, cherry picking a commit from one branch to another. I am Matthew, CRASX crash on Drupal. I am a Denver transplant from Chicago, did a BS in computer science. I survived somehow at UIC. Started playing with Drupal around that time, Drupal 7. I'm a lead developer at Bounteous, do a lot of DevOps stuff, love diving into the weeds and into operating system level things. I'm also disabled. I have a disability called cerebral palsy. If you have questions about it, feel free to find me at the happy hour. I work for a company called Bounteous. Hi. Bounteous is a digital agency. We're based out of Chicago. We have offices everywhere. We have an office here in Denver. We're a remote first company. We do everything from Drupal, AEM, strategy, analytics, all that fun stuff that help businesses win. So a little bit about you. I'm making some assumptions here that you're technical. So have you all used Git before? Okay. Familiar with the command line, familiar with Git, that's great. This talk should be pretty helpful and interesting, hopefully. So a lot of my slides are gonna have shell code on them. Commands that are executed are uncommented. The output from those commands will be commented. So this is a VS Code snapshot. So the green stuff is all the comments. That's all the output. So on the slide, we're making a new Git repository. Initializing it in this directory. When we do that, we create a hidden .git directory that has a whole bunch of files in it, which ultimately stores your data. So the source code for all these slides is online on GitHub. If you want to follow along or go back and look at how this was, you can do that. There's also a short link there. And these slides will be available after this talk as well. But with that, let's get into it. Get in the group. I promise that's the only Git pun in this talk. I'm not that clever. So Git is an open source version control system. Essentially, it's used to track changes to code over the lifetime of a project. It was created by Linus Torvalds in 2005. That name sounds familiar. It's the dude who made Linux, and he actually made it for the Linux kernel. It's also used by Drupal to track Drupal core changes and contrib modules. So anytime you contribute, you're likely using it. And that being said, it's the most widely used version control system in software development. So the way that Git works, we have a working directory, we have a staging area, and then we have our repository. So the working directory is where all your files are. It's where you're making changes. It's where you're running your Docker, DDEV commands from. As you're making these changes to code, you take those changes that you want to commit into your history, and then we move them into a staging area. And then from the staging area, we turn them into a commit, and they get moved into the .git directory. So we're going to talk through what's happening essentially as we go through these steps. So we're going to be looking at objects, and objects are the brain of Git. So if you look at what's in our Git directory, under the objects directory, there's a bunch of these long hashes. They're stored in their own directory. So the directory is the first two characters of the hash, and then the rest of the hash. So each one of these is its own object. You'll notice that there's no file extension on these objects. So if there were to be a readme.txt file in here, you're not going to find .txt on that object extension. And we'll see that objects have different types. So there's a blob, a tree, and a commit, and these all come together to ultimately track the data of your history, the history of your data, other way around. So those hashes that we're seeing in that objects directory are hashes of content, essentially. So each one of those object IDs represents a piece of content. So Git gives us this really interesting command to generate a hash from whatever we want. So if we give it the string hello world and run hash object, we get this 557 db0 hash. And when we run that command, an object gets created on this with that same hash. And then we can also take a look at the contents of that hash, like us. Yeah. Actually, let me just go back first. Okay, so the hash, typically you're going to see a 40-character hash. That is a SHA-1 hash. So it's a SHA-1 hash of like hello world. There's some extra data around it that it hashes as well. But newer versions of Git might use SHA-256, so larger hashes. Objects can be referenced by a partial hash. So Git gives us this cool command cat file. So cat file -p means pretty print the content. So if we give it that hash that we just calculated for hello world, we'll get that string hello world back. And we can reference that hash by the beginning of it. So 557 db0 is the same hash. You can even say 557d. As you get more objects in your database, you'll have more collisions, and you'll have to give it more characters to make sure it's unique. And so a blob object is essentially this. It's the contents of a file, only a single file at a given point in time. So let's see what that looks like when we stage content. So if we take that string hello world, put it in a readme.txt file, run git add. Git add will take that file from our working directory, put it into our staging area where we can get it proper for commit. Git status will show us what's in that staging area. So we'll get a breakdown of things that are ready to be committed, things that aren't ready, and kind of where we're at in our workflow. And then git ls files is a really cool command that essentially gives us the entire contents of what is in our staging area. So if we put that string hello world and read.txt, run a git add, and then run git ls files, we'll see that we have a single line with a little bit of data on it. So every entry in our staging area is going to start with our permission bits, which are Unix execution bits. We'll get the object ID. So in this case, the object ID is the hash of hello world. So it's that same 557 db0 hash. We'll see that exists on disk. And then we're also going to get a conflict status. So that 0 after the hash is the conflict status. And there's different meanings there. We'll see what a conflict looks like when that happens. And then finally, we have the file name. So that's how Git knows what to commit with your next commit. So if we were to make a directory and add another file, index.html, we can put that same string hello world in it, add it to our staging area. The staging area can hold however many changes you want to put in it. You'll notice that you don't see any directory. You only see readme.txt in this index.html file that we just created. they're pointing to the same blob though, because those two files have the same object contents. So this is one of the ways that Git saves, saves on data usage and calculations, and that it's sharing the objects between these two files because they have the same content. And that has some really interesting implications. But before we get there, we'll talk about committing. So we have all our files in our staging area. We run a git commit. That commit is going to make another object in our objects database. So we have another hash. It gives us on line 73 that ECDBE hash. And we'll see that once you run that commit command, it gets created on disk at that location. So commit snapshot changes. It's a snapshot in time of your repository. So regardless of what Git doesn't care about what has changed in your latest commit, it only cares about the contents of your file. So it's going to take all your files in your staging area, put them into a commit object. And then if we go back and kind of look where we're at, we'll take a look at what that commit object holds. But we had our change, put it into our staging area. We just ran our git commit command. Those changes are going to be put into our repository and made permanent. So if we look at the commit object via that cat file command, we'll see the commit object itself is going to contain some information about the commit. So we have our committer information, committer and author. We have that commit message, my first commit, that we just gave it. But then we also have this tree, and this tree is another object. So this commit object is pointing to another tree object. And then again, the object ID for this commit is the hash of all the content that was printed in that command. So that's the string, it's stored as a string like that in the Git history, and the hash, or the ID of that content is the hash of that content. Yeah. So if we take a look at that tree object again through the cat file command, we'll see something a little bit different than our staging area. So we have a blob that's our readme.txt file pointing to our 557db0 hash. And then we also have another tree object. So, and it's pointing that to that other tree via the doc group. So again, if we take a look deeper, run cat file on that doc group, we'll see that we have index.html with our 557db0 hash pointing to that object. So if we look at the difference between our staging and our commit object, in our staging area, every one of our files is going to be listed regardless of whether or not it has changed. So this is how Git knows the current status of your repository. Is it if we're on that commit and we update the readme.txt file on line 101, run a git add, and then run that ls files --html, we'll see that we still have docgroup/index.html pointing to that hello world blob. But now the readme.txt is pointing to a different blob because it has different contents, and that blob is the hash of Git rules. And then take that, make another commit. We go through the same process. If we take a look at this last, this is all not helpful. So if we take a look at line 111, if we take a look at the commit we just made, we'll see that we have our commit object. But on line 113, we have this additional line that is the parent, and that is telling Git that this commit came from another parent. So if we take a step back and look at the entire picture of what we just did, so we have our first commit. That commit is going to point to a tree and then point to the hello world blob via both readme.txt and docker/index.html. When we make our second commit, it's going to point to a new tree where readme.txt is pointing to that hello world blob, but it's also going to point back to this original tree because the contents of this tree have not changed, so they have the same hash. Anyone have questions about this? I don't know if anyone's in. Maybe. Yeah. Any questions on this? Before I continue on, we're going to be talking about merging branches and combining branches next. So, let's talk about it. Get ready to merge some stuff. Oh no, another one. How could I? So, we're going to be setting up a scenario here where we're going to be combining these two branches. So this main branch in shape is our, the last part of our presentation. We have my first commit, my second commit. We're going to go back and make a new branch off of our first commit, and then we'll update our readme.txt file, make our index.html file a little prettier, and then make another commit for that. So in our main branch, we have, one commit that's different, and then on our feature branch, we have two commits that we've made, so two different work streams that we're working from. And we'll see essentially how to combine these work streams in different ways. So really quick before I do that, I want to touch on Git references. So, everything in Git is an object except for a branch and a tag and maybe some other stuff. But so branches and tags are references, and those references are just pointers to commits, so they're not objects themselves. So branches are stored in .git/ref/head. So if you go in there and cat out that file, you're given just the hash from the latest commit of that branch. So wherever that branch is pointing to. And you can, so you check the feature branch, check main branch, and then you can move branches around because they're just pointers to commits. So on line one, so if we're on our feature branch, on line 180, we can just reset our feature branch to main. And if we cat out, the reference at that point, it's pointing to the same place that main is pointing to on line 178. And then we can, undo that process if we want it to. So when you move that branch, the commits that it was pointing to are still there. All those objects are still in the database. It's just pointing to a different location. So we can reset it back to where it was before, which is that E455 hash, just that same reset command, and then it's back to where it was pointing on line 175. So with that in mind, we're going to be running through a few different scenarios here. So we're going to do merging, rebasing, and cherry picking. So I'll come back to this graph here at the end, but essentially on the right, we have in the orange there, we have our rebase, and then we have our merge in pink and cherry pick in blue. I made tags on all of them so that we can track them and know which one is which, and in the UI it's a little bit easier to see what's happening. But let's start with, I guess I could talk to this. So merging, we're going to take two branches, we're going to combine them together into a single commit, essentially. So it creates what's called a merge commit, and that's what we see up here, which is that 7C6 hash. Rebase, we're going to take a set of commits and then move them to the top of another branch. So we'll see how that works. And then cherry pick is similar to rebase, but we're only going to do a single commit. I guess I should say rebase is similar to cherry pick. We'll get there though. So starting with Git merge, again, we have our original branch set up here on the right. So we have two branches, main and feature/my feature. So for on the feature branch, we run Git merge. It's going to do what's called the ORT algorithm, which is a three-way merge, ostensibly recursive twin. I thought that name was hilarious. It means like recursive twin, but like not really. Never heard that word before. It's funny. So we start with our first commit. So the way a three-way merge works is it will find the common ancestor. In this case, the common ancestor between our feature and our main branch is our first commit. Then it's going to run a diff between that ancestor and the feature branch. And this is what that diff gives us. So on line 189, we have, 191, we're updating our readme.txt file. And then on line 200, we are updating the index.html file. So this diff has, those two changes from that side of the branch, and then it's gonna do the same thing for the other side of the merge. So it's gonna compute the diff between the common ancestor and the main branch that we're merging from. So these two diffs, if we put them side by side, one of them has readme, or they both update readmes, right? So in our original branch, we put git rules in our readme.txt file. In this new branch, we have a little bit more description. We also have the index file being updated. So when we merge these, I guess the diff is the difference between two blobs. Each commit is a point in time blob, so it's just looking at the difference between those two files. There's a really interesting algorithm they use to match up like lines that get moved and like adding lines between other lines. So because of this algorithm, Git is able to recognize kind of like code differences where you're like moving lines around and understanding like how like the history of your code has changed. Okay. So if you look at this, like in our readme.txt file, what this diff is saying is that we're on line 192. We're saying, okay, we're updating, the first byte of this file. We're overriding it. On line 210, we're doing the same thing. We're updating the first byte and we're overriding it. So Git sees this and it recognizes that there's a conflict and it yells at you, and then you make this face. It's great. So after we run that merge command, we get put into this conflict state. So in the conflict state, we'll see that it'll update the readme.txt file to denote what the conflict is. So in our main branch, we have git rules, and in our feature branch, we have this additional information. So when we're in this conflict state, the first thing Git does is it updates that readme.txt file to denote that conflict. And that's how it denotes it, is like with the bunch equals and the bunch arrows. And it actually makes it really easy to identify what has changed. So in addition to that, in this conflict state, if we try to commit without resolving the conflict, Git will say, hey, you need to resolve this conflict before you can make another commit. And the way it knows that there's a conflict is via the staging area. So when we ran that commit process, it put 3 references to our readme.txt file in the staging area. And this is where that merge flag gets set as the third value on each line of the staging area. So and we have our commit objects, and on line 231, we have the 557db0 hash, which is where the hello world string that we're coming from. So that's our parent commit. And then we have two other hashes that represent Git rules and our additional Git description. So this is how Git knows that you're in a conflict state, and how it knows what needs to be resolved. And so if you use something like VS Code or any of the JetBrains suite, you can typically have a tool that will help you resolve these conflicts. So like a Git UI tool that will help you resolve merge conflicts. And usually it'll look something like this, where you have, it'll highlight that there's things coming in from either side. So we have our current change and our incoming change based on what we're merging. And it'll color it for us, and they give us fancy links at the top where we can have these things happen automatically. But at the end of the day, Git doesn't really care about what's in the file. All it cares about is when you run git add, whatever the state of that file is at that time, it's going to put it into a blob and put it into your staging area. And once you run that git add command, that conflict is cleared. We're back to just one redo.txt pointing to that blob. And then we can commit that. So we just resolved our merge conflict, added the file back to stage, ran a commit to finalize the merge process. And that's how we end up with this. So we have, our feature branch here still that has 2 commits. We have our main branch that has 1 commit. I think I merged these backwards, but the result is a single commit that is the combination of these 2 branches. And if you were to look at that commit, you would actually see, using that cat file command, you would actually see that there's 2 parents listed in that commit object. And that's how Git knows that this is a merge commit coming from 2 different places. So you can actually merge multiple branches. There's like algorithms where you can have it merge 20 branches if you want. In that case, the commit object would have 20 parents. So that's commit. I'm going to talk about cherry picking now, which I think is really interesting. So we're back at our original scenario here. And what cherry picking does is it will take a single commit from another branch and place it onto your current branch. So instead of combining all the work together, if you just want to take a piece of work from one branch and put it into the other one, that's what cherry picking is for. So in our main branch, one of the things that we if we're on our main branch, and we want to cherry pick the latest commit from our feature branch into it, well, I guess the one commit back, so with the add git description command. So if we cherry pick that command, it's just going to take, or if we do the cherry pick command on that commit, so the E3, whatever. So what it's going to do is it's going to compute the diff between the add git description commit and its parent commit. So again, like the same diff that it calculated when it did merge. So the same like LCS algorithm, ORT algorithm, it'll compute that diff, and then it applies that diff on top of our branch that we're cherry picking onto. Right? So we're on our main branch. We're cherry picking the git description. It's going to take that one commit, put it on top, and then it also preserves the metadata for a commit. So it'll preserve like the commit message, the author, the original time that it was created, I believe. Maybe not. But we'll see when we do a cherry pick that we actually end up with a different commit hash. So if we're on our main branch here, we just cherry picked, cherry pick the update index.html commit. So we will notice that those two commits have a different commit hash, and that's because that commit object has a different parent, so the hash works out to be a different value. So Git doesn't know that those two things are the same commit. It only knows that at that point in time, the status of the files is whatever is stored in the blob for that file. So the cool thing about this is that you can then cherry pick the same commit multiple times. So if you wanted to, at the bottom here, I just cherry picked the update index.html commit 4 times. Git doesn't care that it's the same commit. It'll yell that the difference between them is there are no differences. Nothing has changed, right? We're going from the same blob, same tree to the same tree, but we have a different parent object now, so the hash for that commit is different. Yeah. So this is where we're at. So that's cherry picking. So we have our our merge commit still. So if a merge was combining 2 branches, and we also have this cherry pick branch now where we started on our second commit and then grabbed update index.html a bunch of times. So that's cherry picking. Let's talk about rebasing. And rebasing is kind of like a combination of merging and cherry picking. So when you say, if you're on the feature branch and you say, rebase onto main, it's going to run that same process where it finds a common ancestor. Common ancestor between our 2 branches is my first commit. And then it's going to cherry pick each ancestor from the feature branch onto the main branch. So it's going to start with add git description. It'll put that after my second commit, and it'll do the same for add file heading. When you do that, you'll have the same merge conflict that we had in the other branch because it recognizes as it's doing that cherry pick that the differences between the 2 commits overlap. So you'll run into that same conflict. You'll have to resolve it the same way. And then there's different commands for rebasing where you continue on with the process. But the ending result is this. So we have our initial commit, we have our second commit that we rebased onto, and then we have our 2 additional commits from our feature branch on top of those. So they're all part of the same history now. It's not 2 separate branches. Yeah, and that is our 3 methods of combining things. So we have our 3 branches here. We started from our first commit, second commit, and then over here, so over here we have the rebase. So we have, we moved our commits on top of our main branch. And then we have our merge commit, where we took those 2 commits from our feature branch and merged them into our main branch, making a single commit. And then the cherry pick is where we grabbed a bunch of individual commits and stacked them on top of each other. That's how we ended up our thing. So in summary, Git is a version control system that uses objects and references to track changes. Git is storing snapshots of files. And I think this was a really interesting realization for me because I've always thought of Git in like the diff world. It's like, to get from one commit to another, like apply these changes. But really what it's doing is it's just storing a snapshot of those files in time at a specific time. So moving between commits is trivial because it's just check out whatever the state of this code is. Commits point to tree objects point to blob objects. A lot of these objects are shared across branches and commits to save processing time and memory. Branches are pointers. Git doesn't care where they point to. You can point them to any commit as long as it's a commit. You can't point it to a blob object. But you can point them, you can move them around. And when you move them around, the objects that they were referencing aren't lost. So unless you do like a delete, if you're just moving a branch, if you're doing like a rebase and you mess something up, or if you're doing a merge and you mess something up, you can always reset it to wherever it was previously. That stuff doesn't go away until you explicitly delete it. And yeah, that's it. So I have the graph here if you guys want to talk through it. Thank you for coming to this. And here's my final pun. Pitter patter, let's get at it. Yeah, if you want to find me, you can hit me on email. Not on Twitter anymore. I'm sorry, X, whatever. Drupal crash. Yeah, you guys got questions? Yeah, check hop in. Cool, I think we're good. Get on there. Yeah, anything you guys have questions about or want to chat about?
So when it's doing the diff, it's actually just comparing the two hashes.
It's comparing the two blobs. Yeah, so if the blobs are the same, they'll have the same hash, and Git will recognize that. If they're different blobs, it'll run that algorithm to compute the difference. Cool. No other questions. Thank y'all for listening to me ramble. I love this. I love talking about this. So if you guys have any questions or want to chat, whatever, find me at the happy hour or wherever. Thanks for coming.